Hi everyone, I'm Takayuki Kotani from Astrobiology Center in Japan. Today, I'd like to talk about our spectrometer, IRD, the infrared Doppler for the telescope, for the Subaru telescope. Yep. So the overview of the IRD instrument is a fiber fed and high resolution spectrometer covering YJ-H band simultaneously at the maximum resolution about 70,000. And IRD has two HRG detector, and the spectrometer is enclosed in the temperature stabilized cryostat, and the optical bench is cooled to 180 Kelvin, and the camera lens cooled to 60 Kelvin. And IRD uses EOM-based original laser frequency comb with 5 GHz frequency span and covering 1 to 1.75 micron. And the unique feature of IRD, one of the unique features of IRD is that the IRD can use both multi-mode fiber and also single mode fiber. And especially the single mode fiber it's very useful for eliminating modal noise. And the RB precision is usually we achieve is at the 3 meters per second. At the 2 meters per second is internal error, and the 2 meters per second instrumental error for M-Dwarfs. And the first write of IRD was 2017. So this is a spectrum, and you can see that we have very broadband laser comb covering almost all of the spectral band. So the science goals of IRD is that the RB survey focused on the mid to late M-Dwarfs, and in the framework of Subaru Strategic Survey Program (SSP), please see the poster of Omiya-san about the detail of this program. It's 175 nights for 5 years, starting from 2019. And we have 150 targets, mother sample, and selected about 60 promising targets. And we have several success criteria, but minimum success is the detection of at least one terrestrial planet around the mid-rate M-Dwarfs. And full success is discovering at least one habitable zone planet with 1 to 10 Earth mass. The extra success is discovery of one or more habitable planets around about Earth mass planets. We have also other goals, for example, M-Dwarf characterization and test follow-up program, and transit planet spectroscopy, direct image planet spectroscopy. But today I focus on the radial velocity survey program. So here I'd like to present our some recent scientific results. So this is the first planet discovery from SSP program. So this is the super Earth near the habitable zone around the M4.5 dwarf Ross 508. Its period is about 10 days, and M sin I is 4 Earth mass. It's super Earth. And semi-image axis is 0.005 IU, and the eccentricity, this one maybe has a large eccentricity, but we need to confirm if it is real or not. And planet is well inside the snow line, but it might be possible that the planet was born outside the snow line and then migrated. So is this planet habitable? So maybe not. It's just at inner boundary, inside the inner boundary of the habitable zone. which are defined by the boundary due to the runaway greenhouse effect. But if it has a large eccentricity, well, it might partially pass the habitable zone in the orbit. And SSP program is continuing, and we have more lots of target and more planets will come soon. So stay tuned. The other scientific recent result is that the discovery of Earth-sized planet around M-Dwarfs at 22 parsec, K2415. This planet was first discovered by the Kepler mission and followed by the test intensive program led by Narita-san and also IRD SSP program. So that's the planet is Earth size but 3 Earth mass and planet around late M-Dwarf 0.15 M-Sun solar mass. And probably we probably need more confirmation, but it seems that no atmosphere and the small amount of water, but need more precise mass measurement for this object. And this is the intensive peer follow-up program of test candidate. So, for example, this is these are the M-Dwarfs ultra short period planets. Two planets. One is 10 Earth mass and one is 3 Earth mass. And the one is that the crossing giant planet around the mid M-Dwarfs. So we have identified that this planet is a giant planet, not a brown dwarf, and the paper is submitted, and we will see the results soon. So from now, I'd like to talk about well, RB measurement stability of IRD. So we characterized the IRD's stability by monitoring, by observing the standard star for several years. And we found that the 2 meters per second is our stability. But 2 meters per second is include, of course, all possible radial velocity instabilities from instrument and the stellar activities, telluric, and etc. But we monitored GJ699 for several years, and also so we found that the radial velocity of loss 509, which has super Earth planet, and both data shows 2 meters per second instrument stability. So, so the question is that where it comes from, this instability. So, what limits the radial velocity stability? So we really want to know where it comes from. So the one of the biggest, largest instabilities of course, comes from stellar activity. But today I'd like to I will focus on the mainly the instrument side aspect. First is the modal noise. So we found that probably the modal noise is smaller than 2 meters per second level, based on the result of the telescope pointing shift experiment on sky. So we intentionally shift the beam position against the fiber core, and the measured the radial velocity shift in function of the angular displacement. And we found that if the angular displacement is within the 0.1 arcsecond, so that the radial velocity shift is smaller than 2 meters per second. So 0.1 arcsecond is okay because we have adaptive optics, and usually the pointing stability is much better than this. So how about teric? Potentially it has 1 or 2 meter/second radial velocity variation due to the systematics of the residual telluric line collected by rapid rotator spectrum. For more details, please see the poster of Kasagi-san. How about the temperature variation? So unfortunately, IRD has a large temperature drift at maximum 0.1 Kelvin, but this only increases the scatter of the radial velocity. There appears to be no shift. And lastly, the laser-com wavelength coverage. So we sometimes see the laser-com wavelength coverage at the changes, and it's especially for the, and in this case, for the bright target, the laser-com is not bright enough for some wavelengths. Lastly, about the single mode fiber operation. So IRD has 2 multi-mode fiber and 2 single mode fiber, and to inject the starlight into single mode fiber, the adaptive optics is very important. But we have extreme AO at Subaru, and we combine the extreme AO and IRD with a single mode fiber. I'd like to show some result. So this is the GZ699 spectrum obtained with a single mode fiber. And also on the right figure, that this is binary, but one primary is a G-type star, and the secondary is M-type star. So you can see that the clearly separates the spectrum, and the spectrum SN is good enough. Okay, that's it. My talk. Thank you so much.
So thanks a lot. How much light do you lose when you inject in the single mode fiber?
So it largely depends on the seeing condition, but if the seeing is good, I think the injection efficiency about 40%, something like that at maximum.
Thanks to the speaker again.